Hi everyone, welcome back to the channel. Let's solve a problem today which is interesting, but at the same time this is not so straightforward. It's a complex problem. But watch till the end. There are plenty of things for everyone to learn. I'm going to cover two cases, two scenarios and solve the problems for both these scenarios. And it is going to reveal some of the concepts and give you some methods and steps to solve such problems. These are the typical problems that you get in IIT JEE or any engineering entrance examinations, partly or fully. And also, this is a pretty solid example or a question for Olympiad guys as well. Okay, so let's start reading the problem. Three identical cylinders are situated in a triangle as shown. Find the downward acceleration of the top cylinder for the following two cases. And we also need to find in which case the top cylinder will fall faster or the top cylinder will have a larger acceleration. The first case is that there is a friction between the bottom two cylinders and the ground. So case one is the friction is here. Okay. But there is no friction between these cylinders. And the case B is when there is no friction between the cylinder and the ground, but there is a friction between the cylinders. Okay. So it is not so straightforward, and we should get started, starting with the case A. Okay. So the first thing you should notice is that since all these cylinders are identical, and if they are stacked like this, then this is an equilateral triangle, right? Okay, so let's call this equilateral triangle ABC. So this is cylinder A and B and C. And this angle theta, so theta is pi by 3. Okay, 60 degree. In this case, all the cylinders are identical, but there could be a scenario where the cylinders are not identical. Okay, so I will solve this problem for theta, and in the end, I will try to put theta as 60 degree and see the answer. Okay, so for case A, the friction is there between the bottom two cylinders and the ground, but there is no friction between the cylinders. And our job is to find the acceleration for A. Okay, so let's first draw the free body diagram, right? So let's take the top cylinder first. Okay, assume this is the top cylinder. Okay, so weight is downward. Let's say the mass of each cylinder is m. There is a reaction force from cylinder B and C here. So let's call it N. Okay, now if you see, if you extend this line, then they will go and meet the center, right? Because this normal force is perpendicular to the tangent here, right? Okay, so let's call this N. Okay, now what is this angle? So this angle we already know is theta. And let's assume that this is going down with acceleration AY. Okay, so this is the free body diagram for the top cylinder. Okay, so let's also draw the FBD for one of the bottom cylinders. So let's say this is C and there is a friction force here. Okay, so let's assume that the friction force is in this direction. We can take any direction. Eventually it will try to correct itself. Okay, let's say that the acceleration here is AX, and this is okay to assume because if this is X axis and this one is Y axis. Okay, this normal force that you see here, according to Newton's third law, they'll be equal and opposite. So this will also meet at the center, and this is also N, right? And there is a weight here which is mg, some reaction force from the ground which is R. Okay, so this is the top cylinder A and this is the, okay, so let's write the F equal to Fy equal to May for A. Okay, so what do we get? We get mg minus 2n sine theta equal to May. Okay, so let's call this 1. And if you write the equation for the cylinder C, and this is going to be Fx equal to Max, right, for C. So f plus n cos theta. So if you see, this is theta, this is also theta, right? Equal to max. So let's call this equation 2. Now we know that the friction is there between ground and the bottom cylinder, so that's why this force is there, and we can assume that it is going to be pure rolling. So friction is enough to ensure that this cylinder pure rolls. Okay, so which means that F into R equal to, now it is basically turning in this direction. Since I have taken force in this direction, so this will become negative, so minus I alpha. And for pure roll, we can assume A equal to AX equal to alpha R, right? So therefore F equal to minus I by R square AX. Okay, and if we put F in equation 2, so then it becomes minus I by R square AX plus n cos theta equal to mx. So therefore n cos theta is m plus I by R square AX. And let's call this equation 3. Okay, so far so good. Now what is the relation between AX and AY? So in such question, you should see how the contact plane is moving when the cylinders are moving. So when this cylinder is coming down, this cylinder is going this side, this cylinder will go in this side. So if you draw the contact plane, let's say this is the contact line, and this is center for A, and this is center for B. And if you draw this line, right, now this angle is 90 minus theta, right? So this is theta, right? And this is 90. So, and this is 90 minus theta. What happens that as the top cylinder is coming down, the bottom cylinder is going in this side, separating. So this plane that you see, think of this. This plane is going to turn like this, right? And eventually it will become straight, right? Perpendicular. So if you consider this as y and this as x, then cot 90 minus theta is x by y. Therefore x equal to y tan theta, and therefore x double dot equal to y double dot tan theta for any theta, which means ax is equal to ay tan theta. Okay, and if we use this expression of ax and put this equation ax in equation 3, so putting ax in equation 3, I want to get rid of ax because we need to calculate the ay, right? The acceleration for top cylinder. So which means that n cos theta equal to m plus I by R square ay tan theta. And let's call this equation 4, right? Now we got the n, and we can put the n in this equation, and eventually we'll get the ay. So from 1 and 4, we have mg minus 2 sine theta, and then we can put n from here, which is m plus I by R square ay tan theta divided by cos theta equal to may, right? So mg equal to ay, okay, so 1 or rather m plus 2m plus I by r square tan square theta, right? Therefore, for theta equal to pi by 3, we get mg equal to ay m plus 2m plus I by r square root 3 square, which is 3, right? So therefore, we get mg as ay, we can take m outside. This is 7 plus 6 I by r square, or ay is g by 7 plus 6 I by r square. So this is for a generic rigid body, not necessarily, let's say, cylinder, but let's say for cylinder, we know that I is half mr square. So I think we should not forget the m here, this m, right? So then ay will become g by 7 plus 6 by mr square into, which is g by 10, right? That should be the acceleration for the top cylinder in case 1, right? Case 1 also. Keep this also as equation 5. We'll see why. Okay. So this is the solution for the case A, where the friction was there between the bottom two cylinders and the ground. Now let's see what happens when there is no friction in the ground, but there is a friction between the cylinders, all these cylinders. Okay. So let's again start with the free body diagram. Okay. Let's say for cylinder A, the top cylinder. Okay. So again, this is, let's say, mg. Okay. There is a normal force from the other two cylinders. So let's say n and n. And since there is a friction force, so let's assume that the friction is in this direction. Again, the direction won't matter. If you pick the right one, it's okay. If you don't, it will automatically get corrected. Okay. And let's take this as friction force. This is for top cylinder A. Okay. Now we know that this is theta. This is 90 minus theta. Okay. Right. And this is also 90 minus theta. So, and let's say this is going down with acceleration ay. So if we use Fy equal to may, then the equation will be mg plus 2f cos theta. So you should see this one. This is theta, this is 90 minus theta, so this is theta. Okay. Minus 2n sine theta equal to may. Now let's take this equation as A. Okay. Now for the other cylinder, let's take this as the cylinder C. Okay. Because of Newton's third law, there will be equal and opposite force here. So N, and then F will be in this direction, right? Okay. This angle is, of course, 90 minus theta, right? This is 90 minus theta. Theta, 90 minus theta. So this is 90 minus theta. Okay. So the equation will be F sine theta plus N cos theta. This is theta. So this is theta. Equal to M ax. We assume that ax is the acceleration. Okay, and we also know that in the previously we figured out that ax and ay are related with this equation, ax equal to ay tan theta, because tan theta is x by 1, right? Okay, so take this as equation B and this is equation C. Okay, now the other equation is that there is no friction force here, so this is the only force which is applying torque, this F, and that torque, if you see, is F into R equal to minus I alpha again, right? Okay, I'm just using this because the actual rotation will be in this direction, right? It will rotate like this. I'm deliberately taking F in wrong direction because I want to show you that it doesn't matter in the end. Okay, this is equation D. Okay, now the tough part here is finding the relation between alpha and R. In the previous case, it was simply alpha equal to A by R, but in this case, we need to see if that is true or not. So again, as I said previously, if you want to figure these things out in the cases where there are forces between two objects and two rigid bodies, and they are moving because of each other, so try to see how the contact plane is shifting. Okay, so here again, if you see what will happen, that if you just consider the figure, when it is coming down, this one will start pure rolling against this one, and same thing A will do against the C, and it will roll like this, right? So it will, as if it is trying to climb up. If you keep this stationary, it will seem that it is trying to climb up, so it is rotating in this direction, but it's not happening because the A is also coming down. Okay, so with this information, let's see how we relate the horizontal movement of cylinder C with the angular movement of the cylinder C as well. Okay, so it's not that difficult to see. Just draw the top sphere A and the bottom sphere, let's say C. Okay, this is A, this is C, and just connect the centers. Okay, and this is where we have the contact plane. Now what happens that because it is trying to climb up, like rotate like this, okay, so in certain period of time this will shift this point and will touch this point, let's say. Okay, so let's draw this like this. Okay, and then this angle is, let's say, delta theta. Now if you explode this one, this view, so it will be something like this, the around the contact plane. Okay, this, okay, this is delta theta, and this one is r delta theta because r is the radius, and this is the horizontal displacement delta x. Okay, and this angle, if you see, is 90 minus theta. Okay, because this angle is theta, hence this is 90 minus theta. So what we get is delta x as r delta theta cos 90 minus theta, okay, which is r delta theta sine theta. Therefore delta theta is delta x by r sine theta, and for a given theta we can just write it as alpha equal to ax by r sine theta if you double differentiate this. Okay, so this is the relation between a and ax in this case, sorry, alpha and ax in the second case. So we can just use fr equal to minus I ax by r sine theta, okay, which is f equal to minus I ax by r square sine theta. Okay, so now we can put this f in this equation B, and we figure out the n. So minus I ax r square sine theta into sine theta plus n cos theta equal to max, and n cos theta is m plus I by r square ax. So pretty much we got the same equation as earlier, and this is also equal to m plus I by r square ay tan theta. So we got n, we got f, and if we put these two in the first equation a, then we should get the ay. So the first equation is mg plus 2f cos theta minus 2n sine theta equal to may. So mg plus 2 cos theta, and f is nothing but minus I ay tan theta r square sine theta, because I just replaced ax with ay tan theta, minus 2 sine theta by cos theta m plus I r square ay tan theta may. So here this one is tan theta by tan theta, so mg is equal to just 2I by r square plus 2 m plus I by r square tan square theta plus m ay. So this is the expression for ay in the second case, mg divided by 2I by r square plus 2m plus I by r square tan square theta plus m. Now in this case tan theta is tan 60 degree, which is √3. So ay is mg by 2I by r square plus 6m plus 6I by r square plus m, which is mg by 7m plus 8I by r square. Okay, so this is g by 7 plus 8I by mr square. And this is the answer for ay in the second case. In earlier first case, this instead of 8 we had 6. So in the case 1, the acceleration is more. So ay is more in the case 1. And for cylinder, this will be g by 7 plus 4, which is g by 11. So in the first case it was g by 10, and in the second case it is g by 11 in case of cylinder. So ay is greater for case 1. So case 1 was when the friction is there with the ground. On the ground there is friction, and between cylinders there were no friction. So there, in that case, the acceleration is faster. And how do you see it logically? So in the case B, if you see, there is a pure rotation happening along this line, right, between these two and these two, and hence there is more energy that is getting transferred for that rotation, that pure rotation, which is absent in the case A. Hence the acceleration in case A is not much, but bigger than the acceleration in the second case. Okay. So I hope you learned few things here. So please do subscribe to the channel, like this video, and share this with your friend. Thank you very much. Thanks for watching. Subscribe and gain access to concepts and tips for doing better in IIT JEE or other examinations. Keep up the great work.